In this video, we're going to talk about how sound waves reflect off of things. So like a lot of other examples, we're going to be using our intuition about other types of waves to think about how sound waves behave when they reflect off of things. Here you can see an example of a wave propagating through a thin medium and reflecting off of a boundary with a thick medium, and also transmitting some of its energy into the boundary with a thick medium. This is just like a light wave hitting a piece of glass with a different index of refraction. You get some transmission and some reflection off of any change in medium. You can actually simulate the type of behavior shown in this picture with two pieces of string of different weight. You can whip it up and down in order to create a wave in one piece of string, and it'll propagate through into the next one. It's also really fun to do with slinkies. That's a really good way to demonstrate this. Now, just like with light waves, the amount of reflection and transmission you get depends on how different the two media that the wave are traveling through are. Which matters a lot for us because our sound waves are mostly going to be propagating through water and bouncing off of things like the surface, so a water-air interface, or the ocean floor or the side of a tank, so like a water and solid interface. And the density of water is really different from both a solid, which is very dense, and air, which is very not dense. So the reflections that you get off of those surfaces tend to be very large. Sound waves in water are almost perfectly reflected off of the interfaces that we mostly deal with. This property of reflection is really useful for sounding. Because waves bounce off the bottom of the water, we can use the amount of time that they're traveling in order to figure out how deep water is. So this example illustrates that. Let's imagine that we're in a boat and we shoot a sound wave straight down, and 1 second later we hear the start of an echo. Based on that, how deep is the ocean? Just as a hint, you'll need to remember the speed of sound from a little bit earlier in this video series. Alright, so go ahead and pause the video and do that. Alright, the answer is that the ocean is 750 meters deep. We know the speed of sound in the ocean is about 1500 meters per second, which tells us that the total distance traveled is 1500 meters, but there's one trick, which is that the wave has to propagate in two directions. It has to go down to the bottom of the ocean, hit it, and then come back in order for us to hear an echo. So that doubles the total travel time, meaning that a wave will travel a round trip of 1500 meters in order to get to the bottom of a 750 meter ocean and then come back. So that example is great and roughly how we'd hope sounding works, but it was a little bit contrived because we only considered one path from the boat to the ocean floor, which is the shortest one, and it looked straight down. However, because sound spreads out like a sphere, it can reflect off multiple different surfaces. That means it's possible for sound to take different paths to arrive at a receiver. In the case of a short burst of sound, that means you'll receive multiple echoes, one for each path the sound could take. Depending on the length of your pulse, these echoes might overlap, which makes it look like one big pulse. And when you see one big pulse like that, it's sometimes tricky to sort out exactly which part corresponds to your direct path. Usually what you do is you just measure your echoes from time of first arrival, but that means you're trying to measure sort of the smallest detectable signal you can come up with, which is challenging. However, the absolute first arrival should correspond with the straightest path from your sound source to your receiver, unless your medium has an obstruction or some weird velocity properties. Now, another way you can do sonar or acoustics is by transmitting a continuous wave. So instead of a short burst, you have a sine wave that's going out into the world. In that case, multiple paths are going to result in constructive and destructive interference, because some of the longer paths will have different phases than your direct path, and those phases could add with your direct path wave or could cancel it. And that multipath interference is actually really tricky to predict. However, that interference is really tightly linked to the distance that your waves travel. So if you take multiple measurements versus distance, then you should see some periodicity in your signal strength. Specifically, your signal strength will be periodic in the wavelength of the wave in the water. You will definitely see multipath in the tank. There are a ton of walls to bounce off of. And because we usually use pretty high frequency sound, you'll need to take measurements more frequently than the wavelength in order to observe this behavior. And we're expecting you to observe this behavior. In fact, if you want to do a little bit of digging, there's an interesting link between the sampling theorem, the frequency of your waves, and how close you need to take these measurements. Specifically, if you want to try exploring this relationship, try substituting V is equal to lambda F into the Nyquist sampling inequality, and pay close attention to the units on either side. So in summary, waves reflect off of different media, and because water is very different from either the ocean floor or the wall of the tank or air, sound waves are going to reflect almost perfectly in the situations you run into an E80. That's great because it lets you do sounding, but it's tricky because it's very easy and common for you to observe multiple reflections of your sound arriving from different paths. And for short bursts, that's going to look like multiple echoes or sort of a spread out pulse. And for continuous waves, that's going to look like interference patterns that are periodic in lambda as you move your microphone around in water.